So this is part 3. In part 1, we saw a brief introduction to the process of glycolysis. In part 2, we learned that in glycolysis, glucose, a 6-carbon molecule, breaks down into two 3-carbon pyruvate molecules in 10 steps. And we saw the basic structures of the intermediates involved in the pathway. In this part, we will learn and write the 10 steps of glycolysis conceptually along with the structures, understanding one step at a time. So let's begin. Before we start writing the 10 steps, let's see what happens in each step and design a blueprint which we can use as a conceptual trick to learn glycolysis so that we do not have to mug up all the 10 steps. We will start by writing the numbers from 1 to 10, indicating the steps 1 to 10 of glycolysis. We will write the numbers in such a way that only 3 numbers are there in one column. As you can see here, 1, 2, 3 in one column, 4, 5, 6 in one column, 7, 8, 9 in one column, and then 10 in the last column. Now we will exchange the positions of 3 and 4. Where we had written 3, there we will write 4 instead, and where we had written 4, we will write 3 instead. Okay, now our skeleton is ready. Now let's blow some life into it. Row 1, that is steps 1, 3, 7 and 10 are ATP exchange steps. In steps 1 and 3, ATP will be used, and in steps 7 and 10, ATP will be given out. In ATP exchange reactions, simple processes of phosphorylation and dephosphorylation occurs. That is, in steps wherein ATP is used, a phosphate group is added to the compound, that is, it is phosphorylated, and in steps wherein ATP is given out, a phosphate group is removed from the compound. That is, it is dephosphorylated. Very simple as that. Next row, that is steps 2, 5 and 8 are isomerization steps. Final row, that is steps 4, 6 and 9 are special reaction steps. Step 4 is splitting or reverse aldol reaction. Step 6 is oxidation plus phosphorylation. Step 9 is loss of water. In step 9, loss of water leads to the formation of enol, that is a double bond adjacent to an OH group. And it is step 6 where coenzyme NAD+ gets converted to NADH2+ during oxidation. You can learn special reaction steps if you want with the mnemonic. Soap, water. S for splitting, O for oxidation, P for phosphorylation, and water to indicate loss of water. And this is the simple blueprint of glycolysis. It will be helpful to learn this and keep this and the general idea of intermediate structures in mind to understand glycolysis. Now let's move on to writing each step of glycolysis. Our substrate is glucose. Let's draw the structure of glucose as we have learned in part 2. A 6-membered ring with 5 carbons and an oxygen, and the 6th carbon with OH outside the ring. To understand better, we will draw straight chain structure as well along the side. 1 C double bond O unit, 5 C OH units, and C double bond O on position 1. So step 1 is ATP exchange step, and ATP will be used. As we said earlier, the role of ATP when it is used is to phosphorylate a compound. That is, add phosphate group to it. So, one ATP will convert into ADP. That is, it will convert from triphosphate to diphosphate, losing one phosphate unit. And this phosphate will get attached to glucose molecule on the free OH site. The OH on the 6th carbon is outside the ring and hence free. So this OH will convert into OP. P represents here the phosphate PO4 3-. Rest everything is same in the structure. Now to name the compound, as we discussed in part 2, consider OP and OH same to conclude the core structure. Here, if we consider OH and OP same, the core structure is nothing but glucose. And it has a phosphate group at 6th position. So it is called glucose 6-phosphate. And this was step 1. Now step 2, which is isomerization. In every isomerization step, what we will do is, we will look for the first COH unit from position 1, as marked here in green, then exchange it with the adjacent different functional group. Like here, we will exchange it with C double bond O. On exchanging the C double bond O with COH, we will get the isomer of glucose, which is fructose. Now let's draw the ring structure of fructose. And the name of the compound is fructose 6-phosphate. This was step 2. Step 3, again ATP exchange, wherein ATP will be used. ATP will come and convert into ADP. Phosphate will attack another free OH on carbon 1 just created by isomerization. As in step 1, OH is replaced by OP. The base structure, considering OH and OP as same, is still fructose. It has 2 phosphate units at position 1 and 6. Thus, it is fructose 1,6-bisphosphate. Now, step 4, which is splitting. It is this step in which 6-carbon compound splits into 2 3-carbon compounds. And this splitting step, step 4, accounts for lysis in the term glycolysis. 3-carbon half with carbons 1, 2 and 3 forms one molecule, and another 3-carbon half with carbon numbers 4, 5 and 6 forms another molecule. Fructose 1,6-bisphosphate is hydrolyzed. Carbon 1, 2, 3 unit forms a 3-carbon ketone, acetone, with 2 hydroxy groups, that is dihydroxyacetone. Again, we're considering OP and OH same for the core structure. So dihydroxyacetone has a phosphate, so it becomes dihydroxyacetone phosphate. The unit with carbons 4, 5, 6 forms a highly unstable gem diol, which immediately loses water and forms an aldehyde, which is glyceraldehyde, as we learned in part 2. It has a phosphate group attached at 3rd position, so it becomes glyceraldehyde 3-phosphate. And this was step 4. Now, step 5, isomerization. We will look for COH and exchange it with the adjacent functional group as we did earlier. If you see the structure formed, it is the same glyceraldehyde 3-phosphate as we saw in step 4. Also, we saw that dihydroxyacetone and glyceraldehyde are isomers in part 2. So, we have one molecule of glyceraldehyde 3-phosphate from step 4 and another molecule of glyceraldehyde 3-phosphate from isomerization step 5. So, in all, we have 1 plus 1 equals 2 units of glyceraldehyde 3-phosphate. So now everything happening in the reaction from this point will be for 2 molecules. Thus, it will be multiplied by a factor of 2. Now, step 6, oxidation and phosphorylation. The aldehyde group is going to get oxidized to its acidic analog. As per the simplest definition of oxidation, that is addition of oxygen or removal of hydrogen, the hydrogen atom of the aldehyde group is removed and replaced by O. Here comes the role of NAD+ or nicotinamide dinucleotide. It is a coenzyme. That means it works like an assistant to the enzyme. Where enzyme alters the structure and the energy of the substrate aldehyde, NAD+ picks up the hydrogen atom and gets reduced. It also takes H+ from water and provides O atom for oxidation. So the product formed from oxidation of glyceraldehyde is glycerate. In this step itself, phosphorylation occurs as well. But this time it is not caused by ATP. Now the molecule is high enough in energy to accept inorganic phosphate directly, which is generally provided by H3PO4. And by accepting inorganic phosphate, it forms 1,3-bisphosphoglycerate. But all this will happen to both the molecules of glyceraldehyde 3-phosphate. So two molecules of 1,3-bisphosphoglycerate will be formed, two inorganic phosphate will be added, and 2 NAD plus will get reduced to 2 NADH2 plus. And this was step 6. Now step 7. ATP exchange and ATP will be given out. Simple. ADP will come, a phosphate group will be removed and picked up by ADP, and ATP will be given out. And this 1,3-bisphosphoglycerate will convert into 3-phosphoglycerate. Step 8, which is isomerization. Again, we'll take the COH group and exchange it with the adjacent functional group. Because we cannot bring carboxylic group in the middle, we will exchange it with the CH2OP unit this time. And after exchanging, it will form 2-phosphoglycerate from 3-phosphoglycerate. Now, step 9. Loss of water, which leads to the formation of enol. H and OH is removed in the form of water as indicated, and a double bond is formed. If you identify the core structure, it is enol pyruvate as we did in part 2. So the compound is called phosphoenol pyruvate. Remember, everything is multiplied by a factor of 2. That is 2 molecules of water is removed and 2 ATP were generated. Now the final step 10, ATP exchange, wherein the phosphate units will be picked up by 2 ADP and form 2 ATP, and double bond will shift for keto-enol tautomerism, forming our final product, that is 2 molecules of pyruvate. This was all 10 steps of glycolysis. We saw each step with structures and conceptually. In next part, we will complete the reactions with enzymes and see the bioenergetics of glycolysis. Thanks for watching and see you in the next part.